Step number 1 is to find the transfer function of this configuration, V out over V in. This will be equal to minus the impedance side between this point and this point, which will be 1 over C2S over the impedance side between this point and this point, which will be R1. Now, if I write things like this, I can go ahead and do an inverse Laplace operation and have that V out will be equal to minus 1 over C2 R1 integral of V in the time domain. Now, this C2 R1 will be equal to what? C2 is 10 nanofarads, so it should be 10 times 10 to the power of minus 9. R1 is 10 ohms, so this will be 10 times 10. So all of this will be equal to 10 minus 7 in the denominator, which will become 10 to the 7th in the numerator, with a minus in front. Now we are ready to try and solve this for these input signals. So let's start with case number 1. If V in is 5, a constant value, then V out will be nothing but minus, as we said, 10 to the power of 7 times the integral of this input signal, which is 5 times t. Okay? This is volts, obviously. Now, before we proceed to the next one, let's make an observation. If the input signal is, let's say this, a constant value of 5, okay, this is 5 volts in respect to time, it is very clear that the output signal will be some kind of line over here, okay, which will be actually very steep, right, 10 to the power of 7 times 5. And this tells me that, well, if this DC signal persists for about 1 second over here, how much will the value of the output signal be, which will be something like this. So the value of the output signals will be, if I replace t with 1, about minus 10 to the power of 7 times 5. So about 50 megavolts. Obviously, this cannot be feasible for a mere op-amp. Alright, we say that it has an infinite gain and it can do many things, but in reality, op-amps cannot get such a high value in the output, especially so soon. Alright, and even if this value was very small, so even if this was 10 times to the power of minus 7, if this persisted for long enough, this would get again very high at some time later, perhaps not in 1 second, perhaps in 100 seconds. So these configurations are not good for DC signals or signals with small frequencies. That means that this has to be fixed, or we have to take care of these DC signals somehow. We can never allow under any circumstance an input of DC value at the inputs. Unless, of course, it's perhaps a square wave which has a very, very, very high frequency. Okay? And only in that case. Otherwise, we must be very, very careful. Now let's go ahead to the second signal, which is what? A sinusoidal wave. So V out will be equal to 10 to the power of 7. Okay? Has a minus in front, but how much is the integral of the sine? It's minus cosine, so this minus becomes a plus times 5 cosine 100 to pt. And all of this will be divided by 100. So we see now that our output is nothing but a cosine, so it is essentially a sine with an angular delay. It's going to have a value of 10 to the power of 5 times 5, the cosine that we found. Now, it's very interesting to see, to pay very close attention to the transfer function. Now, our transfer function in respect to frequency looks something like this, where in small frequencies we get very, very large values, alright? And as the frequencies get higher, the transfer function gets lower and lower. That means that when we work in smaller frequencies, we expect to get a higher amplitudes at the outputs, but when we work in higher, we expect a smaller value. This will work as a very good low-pass filter, but we must be very careful again with the DC signals over here. So this circuit as is kind of working as a low-pass filter. Not very good at that, because these frequencies are very, very small, the ones that we want to pass, let's say, intact on the other side. But for small frequencies, it works just fine, as is. Now, in order to get more of a control on what this does, I have to make a change here, which we will see later on. Again, this change will also fix this issue over here. On to number 3. This signal is something like this. So Vout, working as the same way, will be plus 10 to the power of 7 times 5 over 10 to the power of 6. So it will be something like this, times cosine 10 to the power of 6 2pt. Now, as we predicted previously, the Vout signal is going to be 10 times 5 times the cosine, which makes it much, much smaller than the previous case, where the frequency was much, much more small. That tells me that, well, if we keep going, if we go higher and higher, this output signal will get so small that it will practically not pass at the output. So let's go ahead and go out to our fourth case. Again, Vout will be working at the same exact way. Alright, now this is very important. I forgot to add this 2 pi term over here. So all of this should be divided by 2 over pi. Alright, it's human to make such a mistake sometimes, and even I sometimes, forget it at the first glance. Alright, this means that Vout is going to be nothing but 5 over 20 pi times our cosine, with this high frequency inside. Now, it's very clear that this output signal is very, very small, because this 5 over 20 pi is going to be less than 1. Pi is 3 point something, so 3 times 20, this gets very small. You will see it somewhere, so don't be confused. You may see it in some textbooks. It's going to be 0. Okay, and we say that from there is a point onwards that this out over Vin, V out over Vin, is not getting passed. So this gets so small that the output signal is practically 0 in respect to the input. Okay, now when do we reach this point? Is it exactly when we get less than 1? This is absolute value, of course, and this is also an absolute value. Is it that big of a deal? Don't we have op-amps working with smaller signals? We do, but as an engineer, you have to be able to discern the situations where this thing can be approximated by something like this. If we have been working with smaller signals, of course, this would not be the case. So we must be kind of careful with these things. Let's pay attention to here and understand that throughout all of these signals, we have been having an integrating behavior. Okay, we have been having these outputs in respect to the input, in integral, always. Okay, all right, let's move to the next slide. Now what I've done here is I have connected a resistance R2 in parallel to VC2 in order to fix some issues that have arisen previously. Again, the first step that we have to take is find the transfer function we find it using the same logic. Because this is an inverting op-amp configuration, we have a minus in front. The impedance above sides between these 2 points, which will be C2 in parallel to R2 over R1. 2 in parallel to R2 over R1. How much is this? Minus. By the way, I cannot do an inverse Laplace as is. I'm going to do something else here. I'm going to, first of all, write it like this. And I'm going to pull a trick on you and write the denominator like this. This will be clear why later on. Okay. Now, how much is this thing over here? Let's see. 1 kilo ohm times 10 nanofarads. This will be equal to 10 to the power of minus 9, 10 over here, 10 to the power of 3. All of this will be equal to 10 to the minus 5 in the denominator. Okay, this is 10 to the minus 5, not this. So let me write it once again and replace all values. R2, how much is R2? 10 to the power of 3. How much is R1? 10. 10 to the power of 3 over 10 is going to be 10 to the power of 2, 100. So we're going to have something like minus 100 times 1 over 1 plus s over 10 to the power of 5. Now this is my new transfer function with this configuration. Alright, okay, let's make some observations here. Well, I see that if this s is very small, this whole term becomes very close to 0. So essentially we have something like 1 over 1 times minus 100. Or better, R2 over R1. A typical inverting op-amp configuration, as if this capacitor didn't exist. Okay. What if this frequency gets high enough, very high, much higher than this? Well, this term then overwhelms this term. And this becomes a typical op-amp integrator as we had before in our previous slides. Remember, for the integrator we have now nothing but 1 over s times something times the input voltage. Again, we are going to be having something times 1 over s, this goes somewhere up here, which is a typical inverting op-amp working as an integrator. Now there is an in-between situation where we don't exactly know what happens, but it's okay. Don't worry about it for now. Alright, before I do anything, let me draw the transfer function out of curiosity to see what happens. Of course, this is the absolute value. Now, as we have explained, before we reach a point, let's call this, let's see, 10 to the power of plus 5. This is the omega, okay, the j omega, or s. This is not exactly a frequency, it's the angular momentum, the angular speed. So, we have a constant value up until some point over here, about 10 times slower, so about 10 to the power of 4 here, where we start to fall a bit over here, because these start to become comparable. Remember that this starts to become comparable to this one. And then from that point onward, let's say 10 to the power of 6 onwards, we have the inverting op-amp working as an integrator behavior. We have 1 over s times something, which is the integrating behavior. So from that point onwards, we have an integrating behavior. From one point backwards, we have a low pass filter behavior or low pass amplifier. you can see it like this. It's a low pass amplifier because the output is getting amplified in respect to the input due to the op-amp configuration over here. Again, this will go on up until a point where the output signal is going to be very, very small in respect to the input signal, where we will not have an integrating behavior anymore. We are going to have a cut signal. So this will work essentially as an actual low pass filter. Alright, let's go ahead and try to find the first signal. For inputs of 5, this frequency obviously is 0. That means that this whole thing is 0, so this is minus 100. So the out is going to be minus 100 times 5. Constant value, minus 500 volts. Okay, this is a very large value, but it's not 5 times to the 10 to the power of 7. Okay, that we had before. Alright, remember, previously we had something like this very soon, under 1 second. Okay, in that case we'll have this, but it is constant. And it doesn't get higher and higher as time goes on. This works as an actual low-pass filter, a low-pass amplifier, as we have expected it to work, and it is good, it's good. We have protected our circuit. Let's go to the second case. We have a frequency of 100. So the out is going to be what? This 100 frequency is, let's see, 10 to the power of 2 over 10 to the power of 3. This is very, very small. Again, in respect to this 1. It is not 0, but it's very, very small. It's about 0. Okay, it's very close to 0. In respect to this one, always. So that means that again, what I have is minus 100 times this signal. So 5 times I sine of 100 times 2 pi t, which is nothing but minus 500 times this sine. And this is in volts. So again, we see how prevalent is this low pass filter or amplifier behavior. Okay, we are somewhere along this range. We expect an amplified signal at the output. A cost we have to pay, okay, if we wanted to have just an integrating behavior. For small signals, we are going to pay with having a low pass filter and not integrating behavior. Okay, let's go to the third signal. The out in our case. Now, how much is the frequency? 10 to the power of 6. That gives us from here 10, okay, that is 10 to the power of 6 over 5, 10 to the power of 5, which is 10. 10 is about 10 times higher than 1. Okay, as we have said previously, this is barely at the limit of working as an integrator. Okay, just at the limit. It's barely able to work as an integrator. Barely. We can go ahead and approximate this as minus 100 times 1 over s over 10 to the power of 5. And that's good. So the out is going to be minus 100 times 10 to the power of 5. This is 10 to the power of 7, exactly as we had previously. Remember? 10 to the power of 7. Okay, 10 to the power of 7 times the integrated signal, because this is 1 over s. How much is the integrated signal? 5 over 10 to the power of 6 times 2 pi. Don't forget the 2 pi. Times the cosine. Of course, there is a minus here, so this becomes plus. Be careful with integrating. Obviously, this goes without saying. The capacitor has no initial conditions, so we always assume no initial conditions. We take the integral. It's important to clarify these things. Okay, when we return from the frequency domain to the time domain, when we do integrals and things like that, it's important to remember the initial conditions. This is the simplest case where we don't have initial conditions. Okay, so this thing gives us what? This gets simplified with this. We had 10 in the denominator, 5 in the denominator, so it's 500 times 20 pi. Whatever this is obviously more than 1, okay? So essentially we have some kind of signal over here, amplified, a smaller amplification. This is not 500. Let me write it a bit clearer. This is 500 over 20 pi. So smaller than this, but not very small, so it's more than 1. So it still gets amplified, and it gets integrated. Very, very important. This is volts. Alright, let's go to our fourth case. Following the exact same logic, the output signal is going to be plus 100 times 10 to the power of 5 times 5 over 10 to the power of 8 times 2 pi times our little cosine 10 to the power of 8 2pt. Of course, now, as we had previously, in this case, these get simplified with this, so we have nothing but 5 gets simplified with this becomes 2, so this becomes 1 over 4 pi times cosine. Okay, the cosine that we have had previously. So these things very, very fast becomes very, very, very small and much smaller than 1. Again, it depends on the context of the circuit, but in general we say that, well, in that frequency we do not amplify anymore. So this output is essentially 0. Yeah, as previously, okay, nothing changed here anyway. It's exact same result. This added this resistor didn't change anything. Okay, the only thing that this resistor did is to push forward the integrating behavior somewhere along here and add this low pass filter behavior in the earlier frequencies. Now, how wide this is and how high this is depends on the value of this resistor R2. But the integrating behavior didn't change. This is very, very important. If we were to, let's draw this with another color. If we were to draw the transfer function in case we didn't have a resistor, it would look like this. So it's the exact same transfer function, okay? But we stop this behavior by making it a low pass filter behavior. Okay? Now I know you understood what we did over here. You are a smart person if you have followed along up to this point. I'll go more in depth into the op-amp integrator concepts, so you can check out the playlist over here. Study well, take care, goodbye.